All right, today we're going to look at air resistance and the drag force. How it's defined is a constant times velocity. And you know this about people jumping out of planes, that the faster you go, the more air molecules you hit. And the more air molecules you hit, the more resistance you have to you. So we're going to start with the easy case where you're going at terminal velocity. So when you hit terminal velocity, what's going on is your weight force is completely counteracted by your drag force. The key to this is your acceleration is 0, so that means F net equals 0. So in this case, F net equals 0 equals mg minus force due to drag. So now you've got 0 equals mg minus kv. So mg equals kv. So your terminal velocity is going to be mg over k. So that's a very limiting situation, because that's just telling you what the velocity will be. So that's kind of the first style. The second is what happens when we approach that terminal velocity. So as you approach that terminal velocity, let's take a picture of what's going on with the forces. So I have mg going down, and then I have my drag force going up, but it is not equal in magnitude. It's going to be growing as I speed up. And if you think about how you speed up will be affected by how big the drag force is. So now all of a sudden we have the drag force that's affected by the acceleration, and the acceleration is affected by that drag force. So let's write it out. So F net equals ma. So my F net, as long as I'm in a situation where I'm still approaching that drag force, I have mg minus drag force kv equals ma. So m dv dt. Because acceleration is the derivative of that velocity. So now one of the tricks is to divide both sides by m, and so I end up with g minus k over m v equals dv dt. All right, so the next move is one of the things to do is to get v by itself by factoring out a k over m. And so then by doing that, actually take a negative out, and then by doing that, you now have v isolated, so it doesn't have a coefficient on it. Now, that means my g is going to be, I still have a g there, but now I have an m over k as a negative. So if I were to multiply that back through, I still end up with g. Now, I move my dt over. So it's on top. So I get negative k over m times negative gm over k plus v times dt equals dv. Now I need to get the velocity over this way. So I have negative k over m dt equals negative gm over k plus v dv. So now I'm at a spot where I can actually take the antiderivative of it. So by doing that, I now am going to have something based off of time and something based off of velocity. So when I do that, I get negative k over m t equals, oh, when I move this over, see, I forgot that. It's 1 divided by that. See, thank you. And it was one of you yelling at me for not doing that right. So when I divide that over, it's 1 divided by all that. Sorry, guys. And so now when I take the antiderivative of that, since the antiderivative of 1 over x dx is natural log of x plus a constant. So here it's going to be natural log of x. So natural log of what's in the bottom. Okay. So what I'm going to do, we're going to keep that right here. So I have negative k over mt equals natural log of v minus gm over k. Now, if I want to solve for velocity at a time, I need to get velocity out of there. And the way to do that is to what we call exponentiate. So so like to give you an example, if I have 4 equals natural log of x, I could do e to the 4 equals e to the natural log of x. And e to the natural log is just x. So I have e to the 4th. So that's a way that you can now isolate that out. So now I have e to the negative k over mt equals v minus gm over k. Cool. So now slide it over. So I have velocity equals e to the negative kt over m plus gm over k. And if we go backwards in time, see how this looks familiar? The terminal velocity. Okay, so if I think about this, if I put a very large time in here, a huge amount of time, and it's a negative power, this ends up going away to 0. And so I end up with the correct form. So rarely do you have to do that, but notice that it has an exponential growth involved. All right, more to come. Thanks for tuning in.